Here's our main outline for today. We'll start with the grading example. I know a bunch of you have asked me about grades, and Dr. B, how do I calculate my grade and stuff like that? Let's get down to it. I posted participation data over the weekend, and and I put an announcement, and I put a discussion thread in web courses. This is what the data look like in your grade book. We're going to work on this one. Now up here, academic integrity, don't worry about this one up here. That's not even, I want you all to do that, and I assigned that at the beginning of the semester, summer B, but that doesn't factor into your semester grade. These other ones do. So let's take a look at this one right here. The clicking answers right here. That goes into, that number there tells you how many answers you've clicked in out of the 22 that I've asked since July 5th. All right, the first official day of clicking. I think that was it, or July 2nd, I guess. It was July 2nd. And that goes into this calculation down here. This is actually what goes into your, this is the pointage value out of 25, and I'll show you how to calculate this one. The reason that this is important is because 16 out of 22 for this John Q student here, that is less than 85%. And 85% is the minimum that you must participate to get all 25 questions. Now, you don't have to get 85% correct. You have to have 85% answered. All right, and so I'm going to show you, if you're above 85%, no problema. Ding, you got automatically 25 points. But if you're below that, it's a little trickier. We'll go through that calculation this afternoon. Okay, so get your clicker ready. And let's just start with a simple question. Let me start the... Here's your first question. How many answers must you click in to get 85% or more of 22 questions? So figure that out. Oh, sorry. Okay, got it? All right, great. $20 seconds. Should be a simple calculation, but I guarantee I've tripped up a bunch of yous. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Let's take a look at your answers. Yeah, that's A and C, so C, it's pretty nice, right? But here's something that you may not have thought about. The answer has to be an integer, a whole number. So this one, C, ding, it's out of here. And this is the... This is the correct answer, 19. Now, if you looked at your answer's roundup number and it's 19 or more, ding, you automatically have 25 out of 25 for your clicker pointage. All right? Shh, 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 shh. So technically you can only answer whole number questions. So 19 is the break-even point, or the break point. If you're below 19, we have to calculate it proportionally, and we're going to do that. And my comment to you is that this number 22, right now, 23, because this is our first question of today. All right, so the total for the semester so far is now 23, and therefore the 85% number might have changed. All right, so you just always got to do it. Now, let's go and do a full example of a full grade. All right. And what we're going to do is put the numbers into this grading table. Can you guys come down and sit here below the railing? You're here a little late. I was asking everybody to sit down below the railing. Now let's just make that a general principle for the rest of the semester. And you can just, don't worry about interrupting. Just barge your way in. It's no problem. So this is the theoretical maximum for each one. 50, 50, 50. Best 2 out of 3. Homework 25. Participation 25. Final exam 100. And then this is the amendment we had to put in a couple weeks ago, the lab 60. The lab is supposed to be about 20%. This is the closest I could get with a whole number, some multiple of 10. So this is, my boss said, yeah, 60 is good. 19.35%. So what we're going to do is we're just going to go through an example with John Q. student. Here we go. Let's say that, and go ahead and write these down so you have an example. All right, now you may have numbers like this student, or you may have lower numbers, or you may have higher numbers. But jot these down, and you're going to be calculating iClicker numbers here, or iClicker questions. So let's say that exam 1, John Q. student gets 27 out of 50. God bless America. And exam 2, ooh, he's starting to blaze. He's got 34 out of 50. And I know there's some students in here that dipped upwards for exam 2. That's good. All right, so let's say that those are his 2. Now, let's also say that in web courses and Wiley Plus, he's got 85 out of 90 possible. Now, in this example, I'm not including written homework. Now, most of you have got 3 on the books, 1 in the hopper, homework 4, and 1 more coming this week. And this will be our last written homework. Almost everybody's on the books. So I'm not and because not everybody is in, we can't, put the written homework grades, but next Monday we will. Okay, because you'll have this Thursday a written homework. It'll be graded by Monday, and then we'll be able to do all that. So I'll show you again next Monday how to put the written in. But let's just say right now, 90 question points, total score 90 with everything in web courses and Wiley Plus. So let's say that he's got 85 out of those 90. And we're going to scale that down to 25 points. Now, homework just goes in a straight percentage basis. If you get 100%, you get 25 points. If you get less than 100%, you might get less than 25 points. All right, just percentage. Just multiply by your percentage. And we'll do that in a minute for this guy. But let's get the rest of his specs. Participation in regular lecture. Now, this doesn't include clicking on exams. That's a separate exam score. But regular lecture, and we already know this, for this guy, 16 out of 22 possible. Now, those are the answers. All right? Now, if you recall from the previous slide, he had 15 of those correct. We're not factoring that in. So right now, this guy's got 16 out of 22. Go ahead and verify that on your calculator. Get your calculator going. You're going to need it. 16 out of 22 is 72.7. 2, 7, 2, 7, 2, 7, 2, 7, 2. Anything that's got an 11 in the divisor is going to have repeating decimals. Anyway, so anybody verify me on 72.7%? All right. Now, right now, that's all we've got in for grades. All right? We don't have the final in, but we have some homework, we have some participation, we have 2 exams now. So we can do, what we're doing now is what you can do for the next 2 weeks until the final. All right? And hopefully after next Thursday, or this Thursday, you'll have best 2 out of 3 instead of like this one, it's your only 2 exams. So right now, exam-wise, just 2 out of 2, it adds up to 61. All right, so John Q. student, now next Thursday night, when the exams are graded, he might have a 34, he might have a 35. Then we ditch the 27 and keep the 35, then the 34, then he's got a little bit bigger grade. But for right now, 61. All right, so go ahead and jot that down. All right. And in fact, I'll just pencil it in here for this TOPS merged set of 3 cells. Okay. Now, let's look at the homework. 85 out of 90. Verify me on that. 94.44%. Anybody verify me on that? Yeah. Okay. All right. So what's 94 out of? Go ahead and start. How many out of 25 does he get? Question number 2. Twenty seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right, so C looks like a winner, right? Wrong. Yeah, and here, 23.61 is nice, but I always round up. All right, so that, make a note of it. It's one of the 2 places in the semester where I give you guys a break. I round up. Now, so do not let me catch you napping. All right? Especially when I'm giving you the benefit of the roundup. Now, go ahead and pencil that in. So 24 out of 25. That's pretty good. And a lot of you guys are going to be in that area. A lot of you are going to have 25 out of 25, and more power to you. And some of you will have 24. Some of you will dip down to 22 out of 25. But most of you will be up in the 20s. And you know what? I computed grades over the weekend on the same basis for everybody in a big spreadsheet. And there are only 3 students that have taken all the exams that have an F. And all 3 of those students are either doing zip-zap for participation or zip-zap for homework, or both. If you're doing homework faithfully, one thing for sure, you don't have an F. And I think there's only a few people with D's, so it's looking good. Anyways, so let's figure out the clicking pointage. Now, this is the tricky one. All right? So pencil in 24 out of 25 for John Q. student. And this is the purport. Now, you're going to have to do this on clicker in just a second. So what you do is you form your participation percentage, so for John Q's student, 16 out of 22. And this is whatever you have out of 22 when you're doing yours. Okay, then you divide it by 0.85 over here, and then the baseline score for 85% participation is 25. And so John Q's below 85%. So we have to solve for JQS here. All right, so it's basically this. All right. And go ahead and jot that down in your NOTES. And I want to give you guys chances, but I just go ahead and click this one. How many points? What's his participation pointage based on that proportion? What does the syllabus say? Twenty seconds. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. $189 students. Yeah, you guys are starting to get the. You're starting to get the. What happened? Miss Aftab, what happened? Free. Oh, Lord. Yeah, on multiple choice, whatever you. Your first instinct is usually right. Did you ever hear people say that? Yeah, usually it's right. Okay, so students, here's your calculation. Now, actually, this is John Q. student's calculation. And then here's the second part, Mr. Blanchett. Yes, you round up here too. The two places that I round up are homework pointage and clicking a participation pointage. All right. So, and this one actually comes in 20. If I was going to round to the closest, this one would be 21, but I give you guys a shot. All right. Now, there was a question in the back. No. Up there, Tiffany, the girl next to you. What is your name again? Molly. 21.7. 72.7. What do you mean? You should have gotten 21.39 is what you get when you divide, you work all this stuff out. So you might have had a, yeah. No, that's rounding up means okay, students, listen now. The student is asking me, how come you round it up? Doesn't it have to be 21.5? And the answer to that is, if you round up, it can be 21.00001, and it goes to 22. All right, so that's. Now, the reason I do that is to keep things simple for you guys, give you a little break. All right, so now, all right, pencil that in. 22 out of 25. And many of you will have numbers at least this good. And notice This student, John Q. student, he had a 27 and a 34 on his two 50-point midterms. But these ones come in like another midterm in which he gets a 46 out of 50. And that, my wonderful students, is a nifty chunk of dineros for your grade. And I've mentioned to students, in other words, points, a nifty chunk of points for your grade. And I pointed out to a few students that, oh, Dr. B, I'm really worried about my grade and stuff. But when you actually calculate these points in there, you're not doing so badly. Most of you, if you're here clicking. If you're absent a lot, then it's a little shaky. What's your question over there? I see you talking over, you pointed this in. What's that? Yeah, let's do the lab. Let's see what the effect of the 90% lab grade is. Because like right here, he's doing okay, 71.39. He's within shooting range. He's within striking range of a B, but that actually is a C. Now let's figure this one in. All right, so he's got 90, let's say that he's got 90%, and many of you will have at least that high of a percentage. And I was told by one of the older faculty in the physics department, he said, Dr. B, you young whippersnapper, they're going to have really good lab grades. And it's going to cancel out a lot of stinkiness in exams. And you'll see that in a second. Let's do it. Okay, we're going to add in, so 54 points out of 60. So that goes straight by percentage. And I'll probably round this one up too, I guess. Just so you guys get a break. All right? So now his total goes up to 161 out of 210. And that, my wonderful students, ding, he's broken the 75% level. And there's no pluses and minuses, so that's a B, if I were given semester grades today. All right? So now you know the rest of the grading situation, and you can follow these methods and you basically calculate your grade at any time, except for the fact that the written homework is not factored in yet. Questions over here first. Alexis, not Angela. Okay.
Could you go back to the slide that has how to get the pointage for the lab?
The lab, yeah. The lab grade is just straight percentage. Multiply 90% times 60. Okay. Question?
Yeah. Do you remember like in the beginning of the semester when we got those extra credit clicking points? Should we add that?
Okay. Question is, what about the extra credit clicking points for early registration? Those go in the numerator. All right. So right now, this guy's got John Q. student, 161 out of 210. If he has a bonus point, that goes in the numerator, 162 out of 210. All right? Asia.
Are any of our lab grades dropped like the lowest one or no?
The question is, are any of the... Can you please come and sit down in below the railing, please? New rule. Are any of the lab grades dropped? I have no idea. That's up to what the lab TAs do. They just give me a percentage, and then I do, this. Okay, another question. I know there's a bunch. Okay, over here. Shh, 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 shh. What about the written homework? They will be, but not everybody has had a shot at the 15-pointer. The one that I grade. Okay, so there's going to be a lot of jumble in the grades. So comparing the, you can do it, But, you know, back here on the homework, slide, it's not going to be, what do you do? 90 or so right now we have 3 homeworks. So what do you do? 30? So 120 for that? Or do you add 45? Or no, do you add 35? So that make it 100. So we can't do that until everybody's had their shot at 15. So for right now, but when we do, so next, like I said, on Monday, we'll do it again, and then that number will change again, and it will have all the written homework in there, and then you could just crank, till the cows come home. Yeah. Don't tell me your grades. If somebody. If a friend. Yeah, so then that's going to go, they're all going to add, everybody's got a shot at 10, 10, 10, 10, 15. So it's 55 to, yeah, and I've given the TA the instructions to give a bonus point here or there if he decides it's kosher. And so if you get that, that's also, it doesn't change the denominator. It just changes the numerator. All right, so another question. Go ahead.
So, the first report says we have told the 75% higher, like, of the right question answer.
Yeah, okay, the question is the 4 bonus points for getting 75% of the participation questions correct. Okay, so what you do is you look at the third number. That's your performance percentage, in the 4 that I set up. And if that's above 0.75, ding, you get 4 points. Except we don't ding the bell on those 4 points till till the Wednesday before the final. So, what's that? Yeah, so that would go in the numerator just like all the other bonus points. It would go in the numerator right here. It would go in this numerator. So it'd add to the 1, just like any of the other bonus points. Okay. Another question. Yes, Asia. Academic integrity is not part of the grade for the semester. That's explained in the quiz. It's an activity I wanted everybody to do, but I don't think everybody's done it, I'm pretty sure. Go ahead. No. If you have more than 18 points, you ought just pencil in 25. You don't have to calculate anything. That proportion is only if you're below the 85% level. Right. All right. Let's talk about Doppler shift. This is our last topic from chapter 20. Yes, in the back. Go ahead. That's because includes the final. We don't have the final yet, so if you're trying to, you just gotta, until the final, we don't divide by 310. But right now we can divide by 210. Because we've had 2 midterms, and we've done homework, and we've done participation, so that's 210 out of 310. So this is like a temporary grade. All right. It's an estimate. And it will help you, students, let me, let me just point one more thing out. Figuring out your grade status, the grade pointage and everything, is helpful going into the final. Because the syllabus, can you please let me talk? I'm giving you guys the hairy eyeball the last 10 minutes, and you're still not getting the idea. All right. If you figure out your pointage going into the final, then you look at the points that you need for A, B, C. On the syllabus, you can figure out, okay, to get a B, I need so many points, and I've already got so many points. So in the final, I need to get, the difference of those two numbers. And so that can take some pressure off you if you're worrying about getting an A, or if you're worried about getting a C and passing. All right. And so so going over the grading procedure is helpful for you also in that respect. So you can kind of know where you stand. And for many of you, knowing where you stand going into the final is going to be this. To get a B for the semester, I need to get a B on the final. Or to get an A for the semester, I need to get an A on the final. Or it might be, if you're crushing everything, to get an A on this for the semester, I only have to get a B on the final. Or I might only have to get 81 points out of 100 on the final. Or 77 points. Or you'll be able to figure out what you need to get on the final. All right? So it's pretty nice to be able to do that. And we'll do another example on Monday with all the written homework and stuff factored in. Okay, Doppler shift. There's two varieties of Doppler shift. And I don't know if you learned about it in 2053, but the sound waves, Doppler shift, is a little bit different from electromagnetic. Now, we just looked at the freight train coming around the bend up there in Amsterdam, New York. The CSX freight train. And just type in rail fan in YouTube and you can see about 9 zillion of these. But you have to listen to a few of them before you can hear a good Doppler shift, because the engineer in the train has to cooperate a little bit. He has to blow his horn, as he goes by you. All right, now another sound wave Doppler technology, besides listening to trains, is ultrasound medical devices. Here's a device that I looked up. This is a neonatologist checking the umbilical artery for a little teeny baby, 36 weeks. So yeah, that's something they do, and they use Doppler for that. Here's another one. Dermatologist checking for cancer. He's checking for the speed of the blood and the detection of blood underneath these this bunch of cells up here. So yeah, medical, and a lot of you guys are hoping to get into medical school and so forth, PA school, PT school. So, ultrasound, it's everywhere. All right. So, and a lot of it operates by Doppler shift. Figuring out the velocity of these blood cells and stuff. And that other one is figuring out a blood pressure. Now, electromagnetic waves, it's significantly different. It's similar in that you get a down beat or a down dip in the pitch or the frequency of the electromagnetic radiation as the source passes you by. But the physics is a little bit different because Doppler shift for electromagnetic radiation is relativity. It's a factor, or it's a consequence of the theory of relativity. But we use it all over the place. Weather radar. I mean, how many of you, if you're in Florida, this time of year, you're looking at, this is Hurricane Irma, blazing into Florida about not too long ago. What was it, September? And we missed all those days of school. And God help us. I hope we don't see any more of those Irmas for a while. Another thing, speed. If you've ever gotten a speeding ticket, and I have, so I'm not looking down my nose at anybody, because I've gotten nabbed. Yeah, the cops use a radar gun, and what they do is they bounce a radar beam, a little mini radar beam, off the front end or the back end of your metallic car. And then it bounces back to that radar gun. See, he's got two windows there. One sends out the beam, the other listens for the return signal. And then they compare them. And they're not going to be the same frequency. All right? In cosmology and astronomy, we think about the redshift of galaxies. And actually, homework 4 was about the H alpha line, one of the most prominent diffraction lines, spectral lines in astronomy. Can you please sit down below the railing, please? Find a seat down. What's that? Yeah, please sit down below the railing. New rule. Anyway, so when we look at a galaxy way off in the distance with the Hubble Space Telescope, for instance, thank you for moving. All the galaxies that we see are mostly hydrogen. 74% of the visible universe is hydrogen. So when we look at a galaxy, we see a lot of that red H alpha, 656.3 nanometers. Except it's Doppler shifted because the galaxies are moving away from us. And if you've ever heard of this idea of the expanding universe, that's it. Every single galaxy, except the 3 or 4 near us, are receding. They all, and the further they are away, the faster they're moving. And we've studied that, and we found that that is the evidence of the Big Bang. That all the galaxies, except a couple that are really close to us that we're orbiting and they're orbiting us, everything else is receding away from us. And we see the redshift. As a matter of fact, the redshift that you were working with was for a galaxy about 10 billion light years away. And we could see galaxies way out that far in other objects. So Doppler shift for electromagnetic radiation is pretty important. Now, for both of them, they depend on the relative motion between the source, so the galaxy, or the railroad freight car, the freight train, the locomotive, and the observer. So us here on Earth, or the guy by the railroad tracks filming, or the doctor using the ultrasound. All right? Now here's a picture of a radar. This is a Doppler radar system up on top of a big tower. This is a NASA system. And here it is. Here's a similar unit with the the dome. The dome is basically to protect it from sunlight and rain and the elements and stuff. They're made of like a special material that the radar can penetrate easily. And this thing down here, it's kind of a stop sign shape. My wonderful students, go ahead and write this word down. That's called a phased array radar. Phased array. And we'll study a little bit more about how that works in a couple chapters. I think chapter 27 or 28. And we'll be in 27 on Wednesday before the exam. Now, phased array. See, and here's a couple guys down here. Look at this. See these guys down here? They're kind of shrimpy, but compared to the phased array, so that phased array is maybe 2 or 3 times the size of a human. You know, so maybe 20 feet across, 15, 20 feet across. Now look at this one. Let's go to the next. Now this is a warship, the Chancellorsville. See that? Phased array radar right in the front. And he's got a bunch of other ones up here too. These are the little radars. These are the baby radars. And other domes that they've got up there. CG-62. Now I want you to look at that picture carefully. Just take a look at it. That's a modern day, it's a cruiser. It's not a battleship, it's not a destroyer, it's between destroyer and battleship. It's not an aircraft carrier, they're the biggest. This is a cruiser. Now here's a World War II cruiser from 70 years ago. CA-130, the Bremerton. Now I want you to look carefully at that. All right? Now let's take another look at this. There's Chancellorsville. Let's go back and take a look at this. You notice anything different? What do you notice? Raise your hand. Tell me what you notice. What do you notice in a red shirt? Yeah, the width, it's kind of hard to gauge, but yeah, they're different. They look, this one, it looks tiny, but it's the thing is, it's taken from a sharper angle here, and this other one, a little bit more of a beam angle. What do you see? This one? This is not a Tico. Yeah. Yeah, this is a Tico. It's a Ticonderoga class. Pretty big. What do you see? I don't see any missiles. Wait a minute now. Hold on. I want to hear what you're saying. Tell me more. That's right. Look at this. Look at the gun on this thing. Looks like a pop gun. They just got one. See that up there in the front? That's for shooting seagulls compared to these babies. Oh my goodness. This one, they'll fire a shell the size of a Volkswagen just about.
Yeah, if I had to guess, I'm guessing that this old cruiser is more for, was engineered more for land bombardment and actual sea battles.
Yeah, this one, different era, different technology. So yeah, now look at this one. Look at the weapon systems on this one. All right?
If I had to guess.
What's your weapon system on this one? What's your weapon? That's enough. Okay, please. What's the number one weapon on this baby? The radar. The phased array radar. That's the big thing that they got in the front. Now let me ask you a question. What does that tell you about this? It's a phased array radar too. And you know what else? We got these all over the United States. You think that we love weather prediction? No, there's a reason that we got a lot of these babies all over the United States. So just think about that. Remember, when you're looking at these physical systems, there's a reason. They're there for a reason. You're a doctor, a PA, a PT, a nurse. You're looking at a symptom. It's there for a reason. And diagnosing is trying to see what that reason is. All right, now here's the formula for the Doppler shift. The Z, the redshift. This is what we call the redshift, Z. You know, a redshift is 2.5. That means Z equals 2.5. And it's the change in the wavelength divided by the original wavelength. So the denominator lambda is the wavelength of the police officer's radar gun. You know, the setting in the factory, you know, whatever it happens to be, you know, so many millimeter wavelength radar. Right? Radar is down in the millimeters and centimeters. All right? And then delta lambda is the difference between that and what comes back from your car. Now, if you look at this, if you measure lambda and delta lambda, you can solve that for V. Now, that's a big, monstrous equation. Here's one from the textbook. The observed over the source frequency. So this is a little different notation, and this is frequencies. And they say that FO, what you observe coming back from the car, divided by the source frequency that you know from the factory setting of your radar gun, that's equal to this, approximately equal to this parentheses here, 1 plus or minus relative. Now, plus means it's going away from you, minus means the relative velocity is towards you. All right, so the police officer's got to click between approaching or recede, you know, moving away. But and here's another version of it, in terms of delta F over F, okay, so this is the fractional change in the frequency. That's just minus plus relative speed divided by the speed of light. Now this is for speeds, terrestrial speeds like cars and stuff. You know, something, you know, like a galaxy, we would use the exact formula. And it's easy to invert that formula and get V by itself. You know, the first formula we started with. But this is what a police officer would use. So what they do is they pick up delta F, the change in the frequency by between the outgoing and the incoming return frequency, and that forms beats, okay, in the circuit. And you can measure that beat frequency and figure out everything in this equation and then figure out the relative speed. And then if your speed is above the speed limit, then he tracks you down and gives you a ticket or a warning. You know, whatever he's going to do. All right, so the onboard computer inside that little gun, it's just a little calculator is all it is. It calculates, that's the only thing it calculates is the speed. All right, so that's Doppler shift. Okay, question?
Does this only work when your source is like stationary? One moving and one not moving?
It's V relative, so if both are moving, this will still work. So if the police officer's out on the highway and he's moving at 60 and he measures your speed at 20, the relative speed between you and his car, and it's 20, then that means you're going at 80. And ding, he's going to, you know, so this will, you know, work for, but it also works if he's, you know, like in my neighborhood, they just park at these certain places, you know, out here on Chapman Road, you know, certain times of the day they just park. But they'll do, you know, I did a ride along one time with a highway patrol, and they'll have people out on the highway, just, you know, it's the same formula basically. And you can't get out of it. They get you. I mean, it's pretty precise what they give you. I mean, what the cops have. You know those ones along the side of the road where it says your speed is? Those are like not very accurate. But the ones the cops have, they take very good care of them, and they're well calibrated and stuff. Another question? All right, let's talk about rays and mirrors. And this is chapter 25. A couple things I want to point out to you. We'll do a little bit more tomorrow in the document cam. I can't overestimate to you, or overemphasize, I should say, the importance of this particular diagram. It shows the difference between what we call a wave front and a ray of light, radiation. And the reason that they're important is because light behaves as a particle that travels along a ray, so that the ray is like the path of a particle of light, a photon of light. And then, Helena, the wave fronts give you an idea of the wavelength and the wave nature of light. And so it's important to remember both of those properties. Light has, in the book it says light has a dual nature. That is incorrect. Light has one nature, and its nature is to behave like a particle and as a wave simultaneously. So, Jade.
Are electromagnetic waves the only waves that behave as both particles and waves?
Yes, sound waves don't. Sound waves, we don't think of a particle of sound, but we do think of a particle of light, the photon. And it's, Sir Isaac Newton, the word for it is corpuscular. Corpuscular means corpus, body. Okay, a body or an object. So he thought that light was a set of little teeny BBs that you couldn't see, but that would cause things to light up and stuff. But then another guy, Thomas Young, roughly contemporary with Sir Isaac Newton, I think maybe a little bit older than Isaac Newton, or a little bit later than Isaac Newton. He proved that light is actually a wave as well. So, and nobody figured out exactly why that was the case, but it actually seems to be the case also for material particles like electrons. We'll get to that next week. Now, the other thing here is the wave fronts, if you're in close to that pulsating sphere, go ahead and make a note of this. In close, the wave fronts will take the shape of your accelerating charges. So if that thing's a charged sphere and it's pulsating in and out, you'll get spherically shaped waves. And you can kind of see kind of a convex shape to these ones in picture A. They're curved wave fronts. Now over here, the plane wave fronts, plane waves, definitely emphasize that word, that phrase in your notes, plane waves. When you're far away from any source, the wave fronts are stacked up like parallel plates, parallel or plane waves, we call those. And just like that image B over there. Okay? And so for us, any ray of light that you see in this room, you are not close to you're not nearly close enough to the filament in the light bulbs, Heidi, to see the curved wave fronts. So everything you see here, we're getting plane waves. Okay? Until it goes through some kind of a barrier or through a gap in a barrier. Okay, and that's called diffraction. We'll be studying that a little bit later this week. Jade, question?
Actually, what you just said.
You withdraw? You withdraw the question? Okay. Okay, good. Let's keep going. Now, here's the law of reflection. For mirrors, this is actually everything. You look for the normal to the surface. Okay, that's the black dotted line. You know, and this is for a flat mirror. All right? And so you draw the normal. And then the incoming ray bounces in at some angle theta and bounces out, you know, theta relative between the ray and the normal. That's conventionally how we do that. We calculate. That's the angle that we think of. I mean, we could think of the other one between the mirror and the incident ray, but this is a little bit easier to work with. Okay, so between the normal and the ray, that incoming angle theta, Marlena, and then the outgoing theta, they're the same. Okay? So for a flat mirror, that's everything. And they're all in the same, you know, it comes in and it doesn't kind of glance off they're all in a flat sheet. And you can kind of see that from this diagram. All right? So they're all in the same plane, and the angle of incidence is equal to the angle of reflection. All right? Now, this is actually the explanation for every other mirror. Now, flat mirrors are helpful. We have those all over the place. You know, but you know, in your car you have curved mirrors. You know that one over on the passenger side? It says objects in mirror are closer than they appear. That's I can't remember if it's concave or convex. It's got to be, I believe it's convex, right? And objects appear different size because it's not flat. Every flat mirror, they don't magnify. A flat mirror doesn't magnify. If you have a makeup mirror, you know, on one side of it it's flat, and then the other side it makes your face look gigantic stuff. The makeup mirror is spherical, very big radius of curvature. Telescopes, like Sir Isaac Newton, he figured out how to make a reflecting telescope to gather light rays, and focus them and make them more intense, make them sharp and bright. Parabolic mirror. All you do, and all these curved mirrors, all you do is you think of every little pixel of the mirror as a tiny flat mirror. And then the ray that goes into that pixel, angle of incidence equals angle of reflection, but then you got to do it for all your other pixels in the mirror. And every pixel is going to be at a slightly different tilt, depending on whether you have a parabola, a sphere, or a hyperbola. Now, a parabolic mirror, anybody know where those are used? Parabolic mirror? Yeah, searchlight, a spotlight. Okay, you put a spotlight. It has a very narrow focused beam. You know, so if you're in the lighting crew for a stage play and they need a spotlight, that's what they use, parabolic mirror. Hyperbolic mirror, also used for telescopes. My wonderful students, the Hubble Space Telescope is a hyperbolic mirror. Now, hyperbola, parabola, and circle, they're all what we call conic sections. And if you remember from your trig class, you take a cone, an upright right cone, you make slices through it, you get parabolas, hyperbolas, circles, ellipses, straight lines, and even a point is cutting through right at the vertex of the cone. And so all these different shapes, it's basically counting every little pixel as a little teeny flat mirror. And then just, you know, adding them all together and figuring out where the light goes. Now, here's where the light goes for a spherical mirror. Okay? If it comes in parallel to the optical axis, okay, so line CB, C is the center of curvature for the sphere. And it's a spherical mirror. Okay? And so if the light ray comes in parallel to the optical axis, so you have that spherical mirror, and you know that's the symmetry axis. You know, so you go to point B, the furthest point on the sphere away, Christian, and then you do the normal to that, and that's the optical axis or the optic axis. So if this red ray up here comes in parallel, it's like hitting a little teeny flat mirror up here, except the flat mirror is tilted. So the normal to the flat mirror is segment AC. So make a note of that. And this is a diagram from your book. I forgot to put the diagram number, the figure number, but you'll see it in chapter 25. And check this out. Ding! Angle of incidence equals angle of reflection. And where it goes is to the focus, the focal point, F. All right? And every ray of light near the optic axis and parallel to the optic axis will bounce off the mirror and go through point F. Okay, that's one of the rules for spherical mirrors that you're going to read about tonight that we'll sketch out. Here's another one. Paraxial rays. Are those rays that are fairly close in to the center, and fairly close to the optical axis? Okay, so this guy up here is not a paraxial ray, but this one down here is. And the rule is, if you're in close to the optical axis, if your rays are parallel and paraxial, then they'll bounce right back to the focal point. Now this one up here, this second ray up, it's a little bit far out, and angle of incidence equals angle of reflection means you're a little bit off from point F. Now, over here, I forgot to mention, the focal length, that's the distance from B to F, that's equal to 1/2 the radius. Okay, and the radius is from point C, the center of curvature, out to the spherical. All right, and there's a bunch of different rules for focal length and so forth. Anyway, so paraxial rays. Now, here's how you do paraxial rays. You know, these ones, they come in parallel and they bounce out, they're outgoing through the focus. Now, if you have a convex lens, spherical convex lens, and you come in parallel to the optic axis, it's nice, but the focus is over here. Focus is on the inside of the sphere, you know, halfway from the center out to the spherical surface. All right, so that's good. I mean, it's focused. So what these guys do, they bounce, but they bounce as if they've been shot out from the focal point. So this angle right here, this is your bounce out. This is angle of incidence equals angle of reflection for a spherical convex mirror. All right? And this ray here, if you kind of do a virtual ray back here, it cuts right to 1/2 R, right to the focal point. All right? And that's a diagram in your textbook. And this one too. Now, if you do some rays that are outside the paraxial zone, it's going to get a little sloppy, and that's what we call spherical aberration. All right? But if you're in here close, and here's another reason to understand what paraxial means. If you look at this part of the sphere right here between these two paraxial rays, one above and one below, it's pretty close to a straight line. It's not straight, it's curved, but it ain't far away from being a straight line. Okay? And the closer you get to the optical axis, the remaining curve is straighter and straighter and straighter until you're a smidgen above and a smidgen below, it's almost perfectly flat. Okay? So, and here's how you can understand that. If you have a makeup mirror, you know, or you don't have one, but your sister has one, okay? And they both look, if you're just looking at them, the makeup mirror, the one that magnifies, it looks like a flat mirror. I mean, if it's 10 feet away from you, oh, it's just a mirror. And then the other side actually is a flat mirror. But the one that magnifies, if at a glance it looks flat, but it's not. That means it has a really big radius of curvature. And that means that the paraxial zone, this much, I mean, those kind of mirrors are about this size. And some of them are, you know, little hand jobs like this. Hand mirrors are about maybe this size. The little hand mirrors are about this size, but you're still talking about a fairly large curvature. Okay, and again, here you can see that F, the focal length, is half of R, the radius of curvature. Now, it gets a little fancier for parabolic, and it gets even fancier for hyperbolic, but they have their uses, especially the paraxial versions of each. And by the way, if you were, let me go back to this diagram here. If this were a parabolic mirror for a spotlight, the place that you would, the focal point would be different. I mean, it would have a focal point, a focus, one, inside the parabola, and that's where you would put your light source. And then all the rays of light that go out from the light source get reflected outward, just the opposite of these. And they go outward parallel to the optic axis. You got a good spotlight. All right? Now, we got one more thing to talk about, but before we dismiss, just make a note, read chapter 25.5. We'll do check over those diagrams, and maybe do a few examples. And you know what? Bring some graph paper if you have any tomorrow. Now, I want to tell you something very, very serious. About the grades, the grading situation. And this is by way of admonition. And my admonition is the following. I have detected cheating in recent iClicker activity. For instance, the first page on the syllabus reads, operating another student's iClicker is also cheating. And so what we've got is a tale of two cities. You know, I've got my own way of handling this. Involves no retribution in lecture. I'm trying not to look at anybody. And I'll continue to teach my absolute best, and after today I probably won't speak of it again. I will make my report to the Office of Student Conduct this week. However, for the students that are cheating, there's a different outcome. Those students might not find out that they've been detected until late in the semester, even after the semester finishes on August 3rd. The Office of Student Conduct doesn't move very rapidly, so those students might even continue to cheat. And as a result, they might not know that there's a Z on their transcript or any other sanction from the Office of Student Conduct until after they attempt to walk for graduation. And I will continue to observe. So I admonish all students in here to walk with integrity and let your work be your own. Okay, you're dismissed.